Assalamualaikum, one and all. Today's episode focuses on radioactive dating of rocks using the nuclear transformation of the isotope uranium-238 to the lead isotope 206 and the beta decay of the isotope rubidium-87 to isotope strontium-87. How do we compute the ages of these rocks? Find it out by sticking around till the end of this video. Watch and learn. Question number 1. A laboratory investigation shows that a sample of uranium ore contains 5.37 milligrams of the uranium-238 isotope and 2.52 milligrams of the isotope lead-206. Calculate the age of the ore given the half-life of uranium-238 equal to 4.5 times 10 to the 9th year. As shown in the figure, the nuclear transformation of the radioactive uranium-238 isotope into the stable isotope lead-206 involves a series of 8 alpha decays and 6 beta decays. For our given data, at time t, the uranium ore was found to contain 5.37 milligrams of the uranium-238 isotope and 2.52 milligrams of the isotope lead-206. And also, we are given the half-life of uranium-238, which is 4.5 times 10 to the 9th year, or 4.5 billion years. And our target variable is the age of the uranium ore. In finding the age of the uranium ore, we start by expressing the amounts of uranium-238 in terms of its number of moles. So we just divide its mass converted to grams by the molar mass of uranium-238, which is, of course, 238 grams per mole. Likewise, the number of moles of lead-206 is also computed by dividing its mass, also converted to grams, by its molar mass, that is 206 grams per mole. Take note that this amount of lead-206 is in fact the amount of uranium-238 that has decayed since the time T₀. Alright? And before we can find the time t or the age of the uranium ore, we need to also determine what we call the decay constant lambda. All right, using this formula, decay constant lambda is just equal to the natural log of the number 2. All right, then divide it by the half-life of uranium-238. So once we know the decay constant lambda, we can proceed in determining the time t, all right, which represents the age of the uranium ore. So time t, okay, is computed using this formula, which is the negative of the reciprocal of the decay constant, or -1 over lambda, to be multiplied by the natural log of the ratio capital N sub t over capital N naught. All right? So in this equation, capital NT refers to the amount of uranium-238 at time t, while capital N naught refers to the amount of uranium-238 at time t naught. And this N naught is in fact just the sum of the number of moles of uranium-238 and the number of moles of lead-206. So moving on now to our computations, the number of moles of uranium-238, all right, small n sub u, all right, it is the given mass already expressed in grams to be divided by 238 grams per mole. That is 5.37 times 10 to the negative 3 grams divided by 238 grams per mole. So we get the number of moles of uranium-238 at time t equal to 2.26 raised to the negative 5 moles. Right? Take note that this is the number of what we call the amount of uranium-238, okay, denoted by capital N sub t. So likewise, for the number of moles of lead-206, okay, its mass of 2.52 raised to the negative 3 grams divided by 206 grams per mole, we get 1.22 raised to the negative 5 moles of lead-206. All right? Which we said is actually the amount of uranium-238 that has decayed or transmuted, all right, into lead-206. So that means the value of capital N naught, all right, is 3.48 times 10 to the negative 5 moles. And we got this, all right, simply by adding 1.22 times 10 to the negative 5 moles and 2.26 times 10 to the negative 5 moles. So we got 3.48 times 10 to the negative 5 moles of uranium-238, all right, which represents the value for capital N naught, and 2.26 raised to the negative 5 moles, all right, representing the value of capital N sub T. Continuing with our computation for the decay constant lambda, all right, using this formula, lambda equals the natural log of the number 2 divided by the half-life of uranium-238. Substituting, we get the natural log of the number 2 is equal to 0.693. All right, and that will be divided by the half-life of uranium-238, 4.5 raised to the 9th power year. So, doing our math, we will get this value for the decay constant lambda, 1.5 raised to the negative 10 per year. All right, this also means that in 1 year, 1.5 raised to the negative 10 nuclides of uranium-238, all right, is transformed or undergoes the series of decays, all right, alpha beta decays, all right, in 1 year. So that is how we interpret the meaning of the decay constant lambda. And then computing for the time small t, which represents the age of the uranium ore, all right, whose formula is negative 1 over the decay constant lambda multiplied by the natural log of the ratio capital NT over capital N naught. So substituting, all right, the value of the reciprocal of the decay constant, all right, take note there is a negative sign. So that will be negative 6.7 raised to the 9th power year. And we multiply that by the natural log of 2.26 raised to the negative 5 moles over 3.48 times 10 to the negative 5 moles. So again, doing our math, all right, the number inside the parentheses, or the ratio of NT over N naught, is in fact equal to 0.649 in three significant figures. And getting the natural log of that number and then multiplying it by negative 6.7 times 10 to the 9th power year, we get negative 6.7 times 10 to the 9th year times negative 0.432. All right, that's the value of the natural log of 0.649. So again, we do our math, we finally get the value of the time t, or the age of the uranium ore, equal to 2.9 raised to the 9th power year, which is the same as 2.9 billion years. All right, so that's the age of the rock sample. For our last question, number 2, a sample of rock was found to contain 8.23 milligrams of rubidium-87 and 0.47 milligrams of strontium-87. Question letter A, calculate the age of the rock. If the half-life of the decay of rubidium by beta emission is 4.7 times 10 to the 10th power year. Question letter B, if some strontium-87 was initially present in the rock, would the rock be younger, older, or the same age as the age calculated in part A? Explain your answer. All right, so in this problem number 2, we are talking about the nuclear transformation of the isotope rubidium-87 into strontium-87 by emitting a beta particle. All right. So the nuclear equation is given here, and we represent the beta particle as the negatively charged electron, right? So, just like in number one, at time t, we are given the mass of the isotope rubidium-87 equal to 8.23 milligrams, as well as the mass of the isotope strontium-87 equal to 0.47 milligrams. Likewise, we are given the half-life of the isotope, radioactive isotope rubidium-87, that is equal to 4.7 raised to the 10th power year. And we are asked to compute the age represented here by the time small t, the age of the rock. All right? And the other question, letter B, supposing some strontium-87 was initially present in the rock, meaning at time T₀, there was already some amount of strontium-87. So, whereas if the rock is in fact older, younger, or just the same age as the age calculated in part A, then you have to explain why. Just like in question number one, we also determine the mole equivalence of the given masses of rubidium 87, right? And that of strontium 87, all right? Simply by dividing their respective mass expressed in grams by their molar masses, all right? So, we also take note that the amount of strontium or the number of moles of strontium at time t is in fact the amount of rubidium-87 that has decayed since time t0, right? And likewise, we are also going to calculate the decay constant lambda using the same formula. And of course, the time small t, that represents the age of the rock, all right? Still using the same formula, the negative, the reciprocal of lambda multiplied by the natural log of capital NT over capital N naught. So executing the preceding formulas, we find the mole equivalent for rubidium, all right, equal to 9.5 raised to the negative 5 moles. And this number of moles of rubidium-87 at time t is denoted as the value of capital N T. And for strontium, all right, its mole equivalent is equal to 0.47 raised to the negative 3 grams divided by its molar mass, which is 87 grams per mole. We get 0.54 raised to the negative 5 moles of strontium 87. This is at time t. All right? And that represents also the amount of rubidium 87 that has decayed since time t naught. So, the value of capital N naught, all right, is just the sum of 9.5 times 10 to the negative 5 moles, all right, of rubidium 87 and 0.54 times 10 to the negative moles of strontium 87. So that means our value for capital N naught is equal to 1.0 times 10 to the negative 4 moles. Computing the decay constant lambda, all right, we find it equal to 1.5 raised to the negative 11 per year, which actually means that 1.5 raised to the negative 11 rubidium nuclides, okay, decaying into strontium 87 per year, right? And lastly, computing for the time small t using this formula, all right, we find uh, the value of small time t after substituting and doing our math, all right, we get this value, t equals 3.4 raised to the 9th power year. That is also the same as 3.4 billion years. So that means the rock sample analyzed in problem number 2 is in fact 3.4 billion years old. And last but not the least, our answer to question letter B, it is younger, all right? If strontium 87 was initially in the rock, the amount produced by the radioactive decay would equal the present amount minus the initial amount. So this difference would be smaller than the one computed in part A. Remember, age is directly proportional to the amount of strontium. So that concludes our tutorial for this topic. Till the next episode, mabuhay, mashallah. Thank you very much for watching. Please follow me in my FB page and please don't forget to subscribe to my YouTube channel.